Let's go ahead and do the next example. It's freezing up. All right. So you can see in this example right here, it gives us the molecular formula, which is C4H10O right here. And then if we calculate the IHD real quick, that'd be 2 times 4 plus 2, which is 10. And then so that would be 10 minus 10 over 2, which will be 0. All right, so that tells us that for this compound, there are no rings and no double bonds. Let's say pi bond.
Did they forget or something?
I'm not sure. I know I said 7, and I didn't get any feedback about somebody not being able to come. So maybe they did. I'm not sure. But I mean, it's not like I sent it last week. That was just yesterday, and it was like last night, wasn't it?
Right, and we all stay up at night anyway. So.
Right, making TikTok videos. But it is what it is. We're gonna roll and we can finish these last 2 examples in there, and I'll stop because I don't want to just like be talking to you at you for an hour. So,
Gotcha.
but it's fine. We can finish these examples, and I'll upload the recording to YouTube.
Okay. Thank you.
Yeah. So no rings, no pi bonds, and we got. You can see here. You got 1, 2, 3, 4 signals. All right. So let's go back up to our structures. We already solved this one, right? So we said it was the ketone, right? And then for the other compound, we said that there were no rings or or pi bonds. So there's really only one structure that matches that, and that's this one right here, alcohol down here. So let's see what we got. Let me just cut it, and we're gonna match it up. Come on, computer. All right. So we said it would be 3 or 4 signals, depending on if the OH proton showed up. And so I think for this one, the OH proton did. It is showing up. So that's gonna be right here. Right, so sometimes it shows up, sometimes it doesn't. So we said 3 signals if it didn't show up, and 4 signals if it did. So that singlet out here at I'm sorry, at 3.9, that's gonna be the OH. Right. And you can see the integration is 1 proton. All right. So, and it's not split. Remember the OH proton doesn't couple. So it's not going to be a doublet or a triplet, or it'll only always be a singlet. And most times you can't even make it out because it doesn't even resolve very well. Sometimes it's just like a lump on the on the spectrum. All right. So now we got the three other signals to reckon with, and we can kind of look at the integration and pick them out. So what do you think the signal is here? It's integrating for 6 protons. Which protons do you think that represents? All right, so you got 3 choices. You have this set of protons here. You got a proton here. And then you got the 2 CH3s that are equivalent. So out of those 3 choices, what do you think? Which one of those is going to be 6 protons that show up under one signal?
I might be wrong, but
Okay.
the CH3s.
The ones that are highlighted in blue, yeah?
Yeah.
No, you're right.
Okay.
Right? Because they're equivalent, they're not going to give separate signals. They'll give the same signal. Right? So if you look down here, you can see a signal that has an integration of 6, which is right there. All right. Now, why is it a doublet?
Is it because of the way excuse my cat in the back. Sorry.
I was wondering if that was a cat.
Yes, he's so he's kind of annoyed right now. Is it the way the wavelengths are? Is that why?
So let me ask you this: when we're talking about the splitting patterns, right? Doublet, singlet, triplet. What causes that? Isn't the splitting pattern caused by if you have, let's say you have 2 uh, carbons, right? And you have a hydrogen here. So these R's are different. So that's awesome. So they're not equivalent. Doesn't it split when this hydrogen sees this one and you apply that N+1 rule? So you look at the neighboring protons.
Mm-hmm.
So how many neighbors does this hydrogen have?
It has 2.
No, look at this carbon right here. How many hydrogens are on that carbon?
Just one.
Just one. So it has one neighbor. So for this hydrogen, N is 1. N+1 will be 2. Right? What about the other hydrogen on this side? Now you're looking at the hydrogens that are next door on this carbon.
Uh-huh.
Right? So how many neighbors does it have?
It has
You're only looking at the hydrogens.
okay. You said okay. How many neighbors does hydrogen have? Just one again?
Just one again, right? So N is 1, N+1 is 2. All right. So that's where the splitting comes from. So if you look at the set of protons over here, right? When you look at this CH3, how many neighbors does that have on the carbon next door to it? Right here.
2.
Well, that's only one hydrogen there.
Yeah, the one. Yeah.
You see that? So that's 1 here. And so when it couples with that, for that CH3, N is 1. So N+1 would be 2. It would be a doublet. And the fact that the 2 CH3s are equivalent, you're not going to get 2 doublets. You're only going to get 1 doublet. But the intensity is going to be greater because it's representative of all 6 of those protons. So that's why you see, down here, you see a doublet at about 0.9 that has an integration of 6. Does that make sense?
Yeah, that makes sense.
Mm-hmm. So then we look down here, we got another doublet that has an integration of 2. right? And look at where it is. It's far downfield. It's like 3.4, 3.35, something like that. So if we look at the compound, right, it can't be this proton right here because that's only one. And if that's only one proton, it's not going to integrate for two. It's going to integrate for one. So it has to be the CH2 that's over here. Are you following that?
Yeah, I'm following.
So then, why is that? Why are these protons right here? Why would they be split into a doublet? How many neighbors do you have? Now remember, the OH is not going to count as a neighbor. That hydroxyl proton. So how many neighbors do you have to the right?
You're counting the hydrogens.
Yeah,
You count
only the hydrogens. That's exactly right.
so they would have. Yeah.
So for that one, N is 1, isn't it?
Yeah.
Because it only has this hydrogen right here next door. Right?
Yeah.
So N is 1. So my equal sign is horrible. So that means that N plus 1 is 2. So that's why it's a doublet. And why is it so far downfield? Right? What causes a downfield shift? What? Right? Isn't a downfield shift caused by deshielding when you put a highly electronegative atom around your protons? Is that right?
I think so.
Yeah. When you put the proton in an electron poor environment, it's going to move downfield. Right? So you look at that doublet and the protons it represents, they are those hydrogens are on the same carbon with the oxygen. And oxygen is very electronegative, so it's going to move that signal further downfield. All right, let's do that last signal. We know what it represents. We know it's that one proton right there. How many? What is? How many neighbors does that proton have? So if you were looking at that one proton right here, I'm gonna highlight it again. Right there, you're looking at that one proton. How many neighbors
Would it be
does it have?
zero?
Huh?
Would it be no neighbors?
No, it can't be none now because you got a carbon
Okay.
that's on a carbon, and the next door to that carbon, you got a CH3, and then you got another CH3, and you have a CH2. So it wouldn't be zero. It actually has 8 neighbors. Again, if you look back at the example, the generic example, if I'm looking at this proton right here, I'm looking at the hydrogens on the carbon next door to it, right? So the pink carbon is adjacent, and it has 1 hydrogen. So anytime I need to, I'm trying to figure out how many neighbors a hydrogen has. What I'm looking at is the carbons that are bonded to the carbon where that hydrogen is, right? So that little hydrogen that I have in black right there, it's got a CH3 to the left of it, a CH3 to the right, because this is the carbon right here that I'm looking at. Right, so it's got that proton actually has 8 neighbors. Let me change that color.
Could you explain where the other 2 hydrogens come from? I see where the six hydrogens come from. So where did the other two neighbors come from to make it the 8? That right there. Okay.
Yeah. Because that carbon where that hydrogen is, is bonded to this carbon right here.
Right.
So if it's immediately adjacent, like if it's right next door,
Mm-hmm.
then it's going to be, you got to count them as a neighbor.
Okay.
Yeah. So N for that proton is 8. And that, I don't know why my equal sign keeps coming out crappy like that. So then N plus 1 is going to be 9. Right? And so if we look at the signal, you're going to see that. You can look at that signal and you can count the number of lines that signal is split into. Right? It's, you see those 2 little outside shoulders, you got to count those. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9 lines. Right? For that, you can call it a nonnet, but it's probably easier just to call it a multiplet. All right, questions about that? All right. We know what the structure is. Let's go down to the infrared spectrum so we can pick out some stuff in the infrared. So if this is the structure, right? The main infrared stretch you're going to be looking for is here, the OH stretch, right? That's a very recognizable stretch. It's easy to pick out because it always looks the same. And we characterize the OH stretch as a broad stretch. So it's going to be sorry about that. It's going to be a broad stretch somewhere between 3,000 and 3,300 reciprocal centimeters. Right, and this is probably the easiest out of all of your infrared stretches. This is probably the easiest one to pick out. Pen to work right. So 3,000 to 3,300 reciprocal centimeters. And again, you can see that stretch right here. Look right here. You can see that kind of ugly looking stretch. That's your OH stretch. All right, the only other stretch that matters, well, there's 2 more stretches in here that we can pick out. Right here, that's your alkyl stretching, because you got all those carbon-carbon and carbon-hydrogen single bonds. And then there's one other important stretch to look at, and that's right here. That's your carbon oxygen single bond stretch. That's always going to show up somewhere between 1,000 and about 1,150 reciprocal centimeters. Right? So when you see those infrared numbers on an example on a question, then you'll be able to kind of pick those out. Some of those, so those are really like some of the main stretches. The alcohol stretch, the alkyl stretch, the CO stretch, and then in the previous example we saw like the carbonyl stretch. Like those are like stretches that you should commit to memory, like the range. All right. Any questions about the infrared part? Did you? I did send a infrared video out. Am I right? All right. So I think let's look at the next example. We'll finish this and then we'll stop. All right. So this you can see right here. The formula is C4H8O2. So if we were to calculate the IHD, it will be 10 minus 8 over 2, which would be 1. So that means you got at least one ring or one pi bond. Right? So one ring or one pi bond. So we only really have one other structure that matches that, and that's that ester. Where is it? Right here. Here. Let me cut it. All right, so you got this is the structure for that, right? Because the other ones we can rule out the molecule with the aromatic ring because it has too many degrees of unsaturation to match this the molecular formula. Plus it has a nitrogen in it, and this formula doesn't, right? You can see the formula is C4H10O2. All right, so you got 3 signals and the integration is shown. Which one do you think is which? Let's start with the one that integrates for 2. What do you think? You know it can't be either one of these, right? Because the integration for those is going to be 3. So it's got to be the CH2 that's right here. Is that right?
Yeah.
Mm-hmm. What should it be split into? Should it be a doublet, a triplet? Look at the signal and tell me why it's split into 4 lines like that. How many neighbors does it have on the left?
On the left, it has 3.
Okay, so it's got 3 here. What about here? Right, there's no hydrogens on that carbon. On the carbon on the other side, it has 3 hydrogens, right?
Right.
So for that set N is going to be 3, N plus 1 is 4. So it should be a quartet, which is exactly what you see. And it's integrating for 2 protons, and it's in the location about 2.35, somewhere up in there. It's there because it's next door to a sp2 carbon. Now you got an sp2 hybridized carbon here, and that carbon is next door to it. So those protons are going to be shifted downfield. So remember what we said before, like what are the main takeaways from an NMR spectrum, right? So the first is the location, right? And that's upfield or downfield. And then the other thing that we take away from it is the, I'm gonna say non-equivalence. Non-equivalence. And that's the number of signals, right? That tells us everything that's non-equivalent is gonna have its own signal. So that's the number of signals. And then the other thing we take away is the number of hydrogens. And that is going to come from the integration. All right, so those are like your three main takeaways: the location, the number of signals, and then the other part, the other main takeaway, sorry, is the splitting pattern. Right, so that tells you like the connectivity. Right, what a carbon is connected to is going to determine how many lines a particular signal is going to be split into, a proton signal is going to be split into. So that's why that's a quartet, right? Because it's connected to a carbon with 3 hydrogens on it. What about the other signal at 3.7? What do you think? You can see the integration is 3, so it's got to be one of the CH3s. But would it be the one that's upfield? Or let me take that back. Which one of those CH3s do you think will be furthest downfield based on what it's bonded to? Would it be the CH3 that's bonded to oxygen? Or would it be the CH3 that's bonded to carbon? Right.
Just,
Go ahead.
I'm gonna guess.
Just say it. It's okay. If you get it wrong, it's fine. It ain't but 3 of us in here.
Okay.
Okay.
I'm gonna guess the CH3 that's bonded to the carbon.
This one right here.
Yeah.
Okay. So if it was that one, then it wouldn't be a singlet. Because doesn't that CH3 have 2 neighbors next door?
Right.
So that signal is not gonna be a singlet, right? And it wouldn't be that far downfield. It's gonna be this one, right? Because the O, it's like the structure looks like this. There's an oxygen, and then it's bonded to a carbon that has 3 hydrogens on it. So the fact that the carbon right here is bonded to oxygen, that's going to cause a downfield shift for those protons. So that's why it's so far down. So this can be downfield due to oxygen. And don't be afraid to say something. Just say it. The only thing you can be is right or wrong. And if it's wrong, we can correct it. So that's going to be further downfield. And it's going to be a singlet, right? Because if you look on the oxygen, there's no protons there. And if you look to the left of it, there's no protons to the left of it. Right, so it has no neighbors. So that's why it's a singlet. Right, so N for that would be 0. I should probably color code that to make sure that so that's that. And then the 2, let's make that a different color. Right, and then you only have one thing left is the triplet, which is going to be that CH3 that's on the end, right? Because it has 2 neighbors. And the integration is 3. Right, so that CH3 right here, right, that should be a triplet. N is 2, N plus 1 is 3. Right. All right, what do you think? Yes, no?
Yeah.
Yeah, I think the NMR is one of the more, I don't want to say difficult concepts to think about, but it's just kind of foreign unless you actually work hands-on with it. So it can be kind of weird, but at this rate, I think what we're trying to get out of this is those 4 main points: the splitting pattern, the integration, the number of signals, and the location. If we can master that, then we good. All right, and then if you look in the infrared, which is underneath here, right, you can see the main stretch or signal that you see here is right there, and that's the carbonyl stretch again. Right. So anybody got any questions? I think just working through those 2 examples is enough. There's only 3 of us in here, so I'm going to stop recording and then I'll answer